Okay, so all of you got the exams back. So if you have any questions, some of which I had difficulty understanding what you meant when you wrote. So if you do have any doubts or questions, by all means ask. And if there is, even otherwise, you are welcome to come and talk to me. I would in fact like to speak to each one of you individually, just because I might have, while correcting, I found some comments which I will be happy to give it to you. You can use it. They may be useful, they may not be useful, but you are welcome to hear them and do what you want with them. Okay? Okay. So, and our exam is fixed for the 30th, right? 30th November, right? And so the week of starting 23rd or so, or the 30th is a Saturday, was it, or a Saturday? So that week, the week before 30th is of course exam week for you, right? Okay, so no classes then. The week previous to that, I am not in town. So the week starting 18th, I am not in town. So we'll finish by the week, by the previous week, and wherever we get, that's the course, and you have time until 30th to study for it. Okay, fine. Okay, so maybe I should just discuss the exam questions a little bit. Is that okay? I think it is worthwhile. So, so one general comment is, in the way courses are taught, maybe in CMI, maybe the way this course is taught, maybe at other places, we don't do so many examples on the board, right? For whatever reason, maybe the teachers, in my case at least, the teacher is not prepared to do an example on the board, or meaning it takes time, and somehow, but you're all very good students, so it is expected that you do that at home. Okay, so not just for this course, for any other course. Of course, depends on how you there are various ways of understanding mathematics. There are people who maybe never do examples, but have a different way of understanding things. Maybe there are people who want to do 100 examples before they want to think of the theory, etc. You can, of course, both are. There are as many ways of doing mathematics as there are mathematicians. So, you should choose your way and be, by all means, stick to your way. All the same, how to examples are important for most of us. Okay, if you make a conscious decision that, look here, I don't like examples, I don't want to do them, fine, but that should be a conscious decision. Okay, so for example, this one, something like this was the right. So this is a standard interview question. Okay, what are the semi-simple and unipotent parts of this? Or maybe since the usual decomposition, the multiplicative Jordan decomposition is not talked about, but the additive Jordan decomposition is what it was talked about in linear algebra. So this itself is semi-simple. There is nothing to do here. If you want to write it as s plus n, where s is semi-simple and n is nilpotent, this itself is semi-simple because its eigenvalues are 1, 2, 3. So this itself is semi-simple. Semi-simple means diagonalizable, doesn't mean diagonal. Okay, that's an important difference. Okay. Now, so something like this, that was another one. Maybe that was the third one. Right. Now this is clearly unipotent. So there is nothing to do here. Right, you just write this, its semi-simple part is identity, its unipotent part is itself. Okay, So this is semi-simple, this is unipotent. How about this? The other one given was something like this. Right? Okay. Here, the eigenvalues are 1, 1 and 2. Right? Now, how do you actually find the semi-simple and unipotent parts? You cannot say, this could possibly have a unipotent part and a semi-simple part. Right? Now, I mean, the semi-simple part is going to be, have the same eigenvalues, right? Whatever it is going to have 1, 1, 2 as eigenvalues, right? So, okay, the other thing is, see, some of you have followed, that's not bad at all, that's very good, the proof of how to go about it. Right? So you are given a proof of how to find the semi-simple part and how to find the unipotent part, where the actual proof is given, right? And you followed that proof, which is fine. But the problem with such a thing is that proofs are always sort of bad in the sense of they are built to take care of all situations. Okay, they don't necessarily address the simplicity of a particular situation in hand. Okay, so the other thing that I didn't emphasize perhaps enough is that the semi-simple and unipotent part, suppose you know the Jordan decomposition, right, of a matrix. So if I give you the Jordan decomposition of a matrix, right, what does it look like? It looks like some Jordan blocks, right? These are Jordan blocks. And what does a Jordan block look like? It looks like the same and then once on the, this is a Jordan block, right? This is a Jordan block, right? Now, what are the semi-simple and unipotent? Assume lambda is non-zero, so that this matrix is invertible. So what are the semi-simple and unipotent parts of this? Well, you can now write lambda, 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 lambda and 1, 1, 1, 1. So the semi-simple and unipotent parts of this are lambda, lambda, lambda. This is the semi-simple part, and the unipotent part is 1, 1, 1, 1, 1 with 1, 1, 1, 1, 1 there. That's all right. You can't do that at this level, or worse still at this level, or here, for example. If I write 1, 2, 3, take it out and write a 1, 1, 1 in its place, that won't be there. Why not? Because they won't commute, right? So they won't commute. It's tempting to write that. I mean, at first sight, most of us may be, tempted to write, but that's not. See, the point is that thing has to be in the algebra generated by that matrix. See, it is a polynomial. The semi-simple part and the unipotent part both are polynomials in the given matrix, right? Okay, that thing won't be, but here you can do this. Okay, now so you should be able to write this. So what is the Jordan form of this? The Jordan form of this will be, maybe there was a 1 here, maybe. This is a 2 or a 1? 1 maybe. Okay. Did I have there are 2 here? No. 1 everywhere. Okay. Not that that makes any difference, but. Yeah. Okay. So the idea is the simple way is to just write this, try and write this as a Jordan, its Jordan form will have 1, 1, 2, right, and maybe a 1, 1 there, right. In fact, it does have a 1, 1 because if you try its minimal polynomial, it won't be t minus 1 times t minus 2, but t minus 1 square times t minus 2. Okay, so it's bound to, Jordan form will look like this. Right. So the thing is to try and write it in Jordan form. Right. Okay. So you have to find an eigenvalue for, so clearly the standard basis vector E1 is an eigenvector with eigenvalue 1. Right. The standard basis vector with E2 is an eigenvector for eigenvalue 1 modulo E1. Right. So E1, E2 you can keep it, so they span the generalized eigenspace, so to speak. That is the kernel of the linear operator t minus 1 quantity square. Right. Sometimes that's called a generalized eigenspace. So eigenspace means t minus lambda kernel of that. Generalized eigenspace means t minus lambda to the highest power that you require, so that all the t minus lambda to the whatever power the minimal polynomial has in its factorization. Okay, so so if you do this, I just did it. So and this I remember because I just worked it out. So let me write that. So these are eigen. So if I try 5, 3, 2, let's see what 5 becomes. So I claim 5, 3, 1 is an eigenvector for eigenvalue 2. So this is, if I multiply this by this, I get 5 plus 3 plus, oh, this was a 2. Oh my God, this was 2 and 3. Sorry again. Okay, so that 5 and 3 plus 1, that's 10. That's 2 times 5. Here it is 3 plus 3, that is 6. That is 2 times 3, and finally 2 times 1, that's 2. Okay, so this is equal to, if I write this, okay, I claim I get this. So I write this because, see, this 2, remember this last column 2 just is representing the fact that this is an eigenvector with eigenvalue 2. So if I have a column here, so with 0, 0, 2, that means this column gets multiplied by 2. That's exactly the statement that this is an eigenvector for this matrix with eigenvalue 2, right? And this, the fact that this is 1, 0, 0 is just the fact that this is an eigenvector with eigenvalue 1. And this 1, 1 represents the fact that this is, if I, the action of on this is 1 and 1 here, right? Okay. So what does that mean? If I write this, so let's put this equal to P, I get P 1, 1, 0, 1, 0, 0, 0, 0, 2, P inverse. Right? Okay. Now, see, the point of it's maybe not emphasized enough, right? The point that you can triangulate every matrix over an algebraically closed field, or you can diagonalize very many matrices like symmetric matrices or normal matrices, etc. What is the usefulness of that? It's useful because it's like choosing an appropriate coordinate system in your coordinate geometry, right? That's the point. So use of a proper coordinate, use of a basis, proper basis is nothing more, nothing less than the familiar thing from school that you very routinely do of if given a problem, you choose your coordinate axis, the origin and the angle at which x and y are, you place appropriately, right, depending on the problem. Similarly, given a matrix or a linear transformation, you write it in such a way that it becomes very simple, right. That's the idea of triangulating or diagonalizing a matrix. Okay. So this we all know, but we tend to forget. Okay, given when encountered with a problem, we tend to forget this. That's why I'm repeating it. So the idea now is what have we done? Instead of writing this matrix, we have transferred the problem to this one. This is in Jordan form, so I know its semisimple and unipotent parts. Namely, 1, 1, 2 is the semisimple part. The unipotent part is 1, 1, 0, with a 1 here, right? And then you conjugate back, right? The idea is to write it like this, and in this form it is, it is simple. So is that clear now, right? So same thing appears again in the next problem. Find a torus of dimension 2 in GL2C containing that, right? Okay, so what you have to do is you write it in a form that you understand, right? You conjugate it so that it comes into a form where you can handle it, and then you know that you handle it there and then transport it back, right? So so semi-simple part, so let's call this A, if A is this one, or G if you want. AS is P1 1 2 0 0 P inverse, and AU is P 1 1 0 1 0 0 1 0 0 P inverse, right? And you can easily compute. All right. Okay. Okay. Then what was the second question? Was what? Co-multiplication. That most of you got it right. I sort of did the exam in a hurry. First I had the 2 by 2 matrix, then I simplified it to the upper triangular matrix. So the co-multiplication, the point, and not much comment is required because most of you got it right. In fact, maybe all of you got it right. So the thing to remember is, at least the way I remember it, the co-multiplication map is the pullback of functions under multiplication, right? That is the thing to remember. G cross G to G, there is the multiplication map. So a function on G can be pulled back to one on G cross G, and these are affine varieties. So the ring of functions of x cross y is the tensor product, is the ring of functions on x tensor the ring of functions on y, right? So it is the pullback under the map. So you take two things. The only comment I might want to make is that in terms of notation, you can be bold in the sense that you can use the same letter for both sides. Okay, so there is no, of course you are welcome to use, depends on the context, but for example, I would write delta of what did I say? Determinant. Okay, so determinant. So if ABC is my matrix, determinant of this is AC. So let's call this A or G. Right, and this is the You can write it like that because delta is a algebra homomorphism. Algebra homomorphism. Now delta A is this coordinate, right? So what it means is you have this. So I take two matrices, multiply them and see what I get here, and then take its first coordinate, right? That's what it means. If I have something here and something here, multiply them, they are upper triangular also. Therefore, when I multiply them, the first coordinate of this is just the product of the first two coordinates here. So delta A I can write as, so that's A tensor A. And this I can write as by the same C tensor C. This is AC tensor AC. Right? Or you could write, determinant G is, you pull back the determinant of G, that becomes the product of these two determinants, and then you can write the, however you write it. The determinant of the first one times the tensor determinant of the second one. The determinant function here is AC. The determinant function here is AC. That's another way to do it. Okay? Okay, but point is, it is the pullback under the multiplication map. That's what you should keep in mind. And similarly for all the other things, for the antipode, it is the map at the level of functions of the inverse map at the level of the group, okay, and so on. And one more thing is that it's an algebra homomorphism, right? So the co-multiplication is an algebra homomorphism. The algebra homomorphism is a respects the co-multiplication. Okay, what was, could you please remind me of the third one? What was it? Okay, spectrum of the group ring, yeah. Okay. So the G was given, so group, so this was the group given to you, right? Group ring of this, we write like this. I don't want to write a K round bracket because I'm not thinking of this as an algebraic group. I'm not thinking of that as a variety, right? So now I write this, or if you want to call this, G, let's write KG, right? And you might want to shift to a multiplicative notation. So G is a cyclic group of 60 elements, and you may want to denote this cyclically by your elements being 1 zeta or zeta square up to zeta to the 59, zeta to the 60 being equal to 1, right? Cyclic group. So, and then you take the spectrum of this, and then you take the spec of that, right? And so the thing to observe is that we have what was the one-to-one correspondence, and most of you did see the point, the one-to-one correspondence between diagonalizable groups on the one hand and finitely generated abelian groups without p torsion on the other. Okay, so here it is a finite abelian group, so it is definitely a finitely generated abelian group. Now if it does not have p torsion, then I know that the spectrum of the group ring is diagonalizable. So you just have to observe when it doesn't have p torsion, clearly when p is not equal to 2, 3, 5, right? So is diagonalizable when characteristic of K not equal to 2, 3, 5. Always K equal to K bar, right? That's the situation. Now, okay, identify the group, right? So one thing you could do is the following. You could write this kg itself like so. That's a good. Right, because that's if you write it multiplicatively, then you can write this. Right, now the spec of this, what is the spec of this? It is just where can you send t, right? Spec of this or maximum spectrum of this, when k is not equal to 2, 3, 5, this is going to be a reduced string. That was the point, right? The reason why this is not fails to be diagonalizable in these cases is because this fails to be reduced, right? But if we are off these values, then it is reduced, right? Okay. In other words, what it means is that there are 60 distinct roots of unity, right? There are 60 distinct roots of unity, and therefore that is the group, right? There are the 60 roots of unity of this, right? And what is that? If and what is the group structure? It is bound to be cyclic, because I mean, there is a, you must have seen this. Finite, say that again. Finite subgroup of K stars are cyclic, right? Do you remember the proof? Huh? Well, different ways. So the proof, for example, in Serre's book of this goes as follows. So so you observe the fact from the field that you observe is that given any divisor, say take 60, right? If I take a subgroup of order 60 of K star, right? Now if I take say 30, how many elements have order 30? They are precisely those which satisfy the equation t to the 30 minus 1, right? So there are no more than 30 elements. There are precisely 30 elements. So so the point is, therefore there is precisely one subgroup of any given a divisor. There is precisely one subgroup of that order, and if that is a characterizing thing for cyclic groups, okay, which you can prove by anyway, I've said enough. So if you have a abelian group such that for any divisor, of course you know for an abelian group, although it's not true for any non-commutative finite group, given it's the converse of Lagrange's theorem. That is, if you give me a factor of the order of the group, then there exists a subgroup of that order, right? If there is a unique subgroup of the for every given a factor of the order of the group, if there is a unique subgroup of that order, then such a group has to be cyclic. Okay, so right. So it follows from that this is cyclic group of order 60. So in fact it is equal to that, right? But not I mean, but you cannot blindly say it is Z mod 60. It is isomorphic to that, but maybe there is no canonical isomorphism or anything, right? It is isomorphic to the group you started with, but you cannot say, oh, it is just Z mod 60. No, that's an imprecise statement. Okay, so you should identify this as the character group of this group. Okay, it's the character. It's naturally identified as the character group of this group, and the character group is abstractly isomorphic to this group, but not canonically. So what was the next question? Sorry, I'm forgetting the questions. Okay. So there is not much to say. So this was the element. Okay. Maybe now looking at the answers that you wrote, maybe I should have said the following: give me 10 elements with integer coefficients in the torus, in a torus, all of which are in a torus containing of dimension 2 containing this element. Suppose I give you that question, right? How would you do it? So I want 10 other elements, all with integer coefficients, which must live, all of them live in the torus of this. So again, the idea is you just convert it into a diagonal matrix, and once you have a diagonal matrix, you know the torus there. It is the diagonal torus, right? And then you pull it, you work it backwards. Okay, that's the way I would do it. I mean, most of you have done it. That's not the. I mean, you are welcome to use any which way, but I mean, given the shortcuts and the other things that you sort of employed, I now, if I had to give you the question again, I would have asked you this, so that to have forced you to make you to sort of work a little more. Anyway, so that's done. Then the next one was okay. So then the next one maybe requires some comment, right? So it was given that G acts faithfully on V. V1 is a simple sub of V such that V mod V1 is also a simple sum. Is also simple. The quotient is simple. Okay. And then what else was given? What is the maximal on dimension of a normal unipotent subgroup, right? No, there is some hypothesis missing. This was simple for this was simple for this, right? What was given? Maybe there is a mistake. Okay, fine. Simple G sub. Okay, fine. Simple G sub mod. Okay, fine. Okay. So the idea was that you had this exercise. So we had this ring, whatever, group theoretic angle as we called it, that if you have a unipotent subgroup of GLV, this has nothing to do, again I repeat it, there has nothing to do with algebraic groups. It's just a abstract group theoretic statement. If you have a subgroup that is important, a subgroup of GLV, all of whose elements are unipotent, then they can all be unipotent upper triangularized simultaneously. Okay, this is the so in particular, actually it is enough, and it is enough to show that there is an element which is fixed by all the elements of the group. There is one single non-zero vector at least which is fixed by all elements of the group, right? Okay. Now a little more, suppose you have so the point is, if you have a normal subgroup, so let's call U normal unipotent. So U acts on V1, right? V1 is a simple sub for G, right? Now by group theoretic angle, you know that there exists V in V1 non-zero such that right. Okay. Now consider W or W in V1 such that U W is equal to W. So W is non-zero. This is this, because there exists some non-zero element which is fixed by all elements of V. I consider all elements that are fixed by V, fixed by U, that is non-zero. Now the claim is that W is stable under G. This is the claim, right? Okay. So in general, this is a general fact. If you have a normal subgroup and you take an eigenspace, see, if you take a single element which is an eigenvector for all the elements of that normal subgroup, that may not be fixed, but if you look at that eigen subspace, that will be fixed. Okay. So this is just a very simple thing to check. So for example, let's take G and take W. For W in W, we have to show that W is a G sub. So I have to show that this also belongs to W. So I have to check this, put U, and I am checking whether it is equal to GW. Right? This is what we have to check. Right? So you just use the fact that put a, rewrite it, U is normal, therefore this is another element of U, and therefore this times W is W by the construction of, by the definition of W. So this is equal, so this belongs to U, so this is equal to GW. Now but V1 was simple for G, right? So since V1 is simple, what is the conclusion? W was a non-zero submodule of V1, so W equals V1. Okay, so what you had was, what you get, so this part was an exercise in the book. It said show that, I don't know how it was worded, a unipotent normal subgroup acts trivially on a simple G submodule, G module. Maybe it was asked like that, said like that. Okay. So, and here is the important comment. See, it is not true that this V is V1 direct sum V mod V1. Okay, so here, you might have noticed that there is a visitor giving a course on modular representations of algebraic groups. Okay, the whole point of algebraic group representation theory of algebraic groups in characteristic P is that this does not, such things don't happen. Okay, you would be, so you are thinking, I know where you are coming from. You are thinking in terms of what you know from finite groups over complex numbers, that too, right? Finite groups over complex numbers. So you can write every representation is completely reducible, right? Now it's It comes so much at the beginning, and maybe, but it's a non-trivial fact about finite groups over complex numbers. Okay, if you recall, never have we said anything like that. In fact, it is not true. Okay, the whole point is that even for groups like GLN, for GL1 it is okay, but GL2, if you have things don't have complements, let alone even over complex numbers. For example, if I take this, subgroup over complex numbers, it has a sub, namely for the first basis vector, right? That's a sub of the, so you know what I'm talking about, right? You take this, let's call this B for Borel, so such that A not equal to 0, C not equal to 0, B complex numbers. I mean, in this is a subgroup of GL2C, right? Now, if I have V is equal to E1, or V, so V is equal to 2 by 2 matrices, column, okay, let's say column matrices, right? So you can think of this as a representation of this, rational representation of this group, right? Where, how does this 2 by 2 matrix act on this 2 by 1 matrix? Oh, it acts by, so G, so you have C, I mean EF is, matrix multiplication. Right? Now, you can consider this therefore as a sub representation also of this subgroup. Right? If you do, then the standard basis vector, the span of V1 is equal to E1 is a B submodule. But does not have a complement. You can't find a complement. What will the complement be? You will have to write it as something times x plus something times y. But you can check that nothing like that will be the only thing that is fixed by B is E1. I mean, there's no other sub, right? So yeah, that's easy to see. So even over complex numbers, the problem, sort of the thing is, if the group isn't finite, even over complex numbers, it is not true that modules must split. Okay, so I mean, what you did was not unexpected or unreasonable, but it just isn't. I mean, it's a good thing to want to guess, but it's just not true. Okay. Okay. However, continuing with the problem, what does that mean? So G itself so you have V here or V1 here and then the rest here, right? So you can write matrices. G looks like G goes into that sub group of GLN, right? If I write if I choose a basis for V where the first few basis vectors are V1 and then I extend it to a basis for V, then surely every element of G has a matrix of this form, correct? Because G must preserve V1. So this part is 0. And the rest I have not made any other assumption. Right. Now, but what does U look like? Well, every element of U acts trivially on V1. So it's 1, 1, 1, 1. And by the same token, V mod V1 is simple. So U acts trivially by the same argument, I mean, not argument, by the same statement. Every element of U acts trivially on V mod V1 because V mod V1 is simple for G and U is normal, in unipotent normal for in G. So again here it is 1, 1, 1, 1, 1, 0. But here it could be star. Right? So what is the maximal possible dimension? You get dimension of, you can put arbitrary stars here. Well, that needs to be checked. All you can right now say from this argument that the dimension of V1 times the dimension of V mod V1 is the bound for the dimension of U. And of course, then you have to realize that it is attained. Okay? Even those who have got the answer may have not bothered to prove that it is attained. But that's easy to see because you just take G to be of this form. You know, you take G to be of this form and U to be of this form. Right? So you can check that if I write, see if I write for example, give me, so let me come to that. So this shows, so the dimension of U is less than or equal to dimension of V1 times dimension of V mod V1. That is this size times this size, which is equal to dimension of V1 times dimension of V minus dimension of V1. Right, that gives you the bound. Now you have to prove that it is attained, that bound is attained. Okay, how do you show that? Well, if you given V1 and these two numbers are given, I choose a big matrix, I choose a, this is my dimension of V1, this is my dimension of V, so this is also dimension of V1, this is dimension of V, and put a star here, a GL dimension of GL V1, here GL V mod V1. Right, consider this matrix, you know, or the submatrix of GLV. But I mean, let's fix a, you need not worry about V and V1, you just, the dimensions are important. Just think of all big matrices where this is 0, that is my group, right? And if I take elements of this form, 1, 1, 1, 1 here, 1, 1, 1 here, and star here, that is clearly unipotent. It's also a subgroup, easy to check. So it's a unipotent subgroup and it has dimension equal to this, and it's normal, that's easy to check. Okay, and all the conditions are satisfied. V1 is simple sub of V, V mod V1 is also a simple sub, right? So these conditions are satisfied. So this shows that it is attained. I am not, here I am not saying it is isomorphic, here I am saying it is contained.
Yeah, but why is
It is a closed sub of that G, because G to that, see, G to GLV there is a homomorphism, right? Because V is given to be a representation. And it's faithful, therefore it is injection, and we know abstractly from before that the image is.
Why is the image isomorphic to G?
Okay, even if it is not, it's an injection. Even if it is not isomorphic, never mind. It gives you a bound, right? See what you're, you know. Okay, again it's the same problem, the other problem that we had the other day, right? I mean, why is it not? Yes, correct, absolutely. I'm not claiming that it is isomorphic, but it does not matter. There is a map from G to its image. Okay, so the image of U is like this, right? So image of U is constrained to be like this. Okay, okay, now okay, maybe there is a, okay, I understand sort of your point. Here one of the things here is mentioned is dimension of, so this is good enough, it's okay. So I hope this is a subtle point. I you know, he's asking a very good question, and this question came up also previously when Sayanto asked some question and we tried to discuss it, and then the same problem came up and we decided that there is a mistake in the book, right? So the same so the problem here is the question being asked, and it's a good one, is I'm somehow assuming G acts faithfully on V means that there is a map from G to GLV and it's an injection as a group. It's an injection as a group, but what Abhishek is asking is, why is that an isomorphism of varieties, right? Okay, so I can skirt the issue because in the so the problem is because you could have even a bijection of varieties, a morphism of varieties which is a bijection, but the inverse map need not be a morphism of varieties. That's the point, right? That's where the difficulty lies. But this is a much more coarse issue, so we can get around the point as follows. So if you have G to H homomorphism of linear algebraic groups, right, then image of G, so image phi is closed in, that we saw. Second, dimension of G is equal to dimension of kernel plus dimension of image. That is okay. So if you know that it is a bijection, then the kernel is bound to be dimension 0. Okay, so you are not going to, as far as dimension is concerned, you're all right. Does that answer your question? Okay, so it is a subtle point, but we are not, we can get around it here. So you're right, I cannot think really of G as a sub of GLV. Your point well taken, but nevertheless I can say that the image has the same dimension. Okay, so I can just transfer it to saying the image having the, so I can just throw away G, worry about image, all right, okay, and work with that. Okay, good point. Okay, is that okay? Now there was so the next question was so that was just a standard right out of the book since I had mentioned that you should do that exercise, I decided to put that on the exam, where you were required to show that you can linearize any action. That is, given a variety x, on affine variety x on which a linear algebraic group acts rationally, you can always find a rational representation V of G in which you can put x as a closed sub and include the closed embedding of x in V is G equivariant. Okay? This is sometimes called linearizing an action, because you are reduced to studying. If I study all orbits and are all representations, then I have studied all varieties, G varieties, because any variety is realized as a closed orbit, sorry, not closed orbit, is a closed sub of a rational representation, right? Okay, so let me not go through the proof of that. Most of you got it right. You just choose the idea is to take an set of algebra generators. The idea is the same as in when you say every G can be realized as a closed sub of GLN, right? You choose a set of algebra generators for there you did it for G, here you do it for X. You take a set of algebra generators for Kx, then you know that Kx is a locally finite rational representation of G, and so there exists a finite dimensional representation of G inside Kx containing all these given algebra generators, right? So you take that, and that will be your V, in which you will put your, or maybe it's V star, where you put all your elements. So you choose V is equal to a G finite dimensional G invariant subspace of Kx containing a set of algebra generators. Okay, then you can put, claim is X so G equivariantly. Right, what is this map? X goes to evaluation at X. Right, what is evaluation at X? An element of V star. So to give an element of, so evaluation at X should be an element of V star, which means it should be a linear functional on V. So I take an element of V, call it F, because I can think of it as a function, as a sub of Kx, so I can think of it as a function, so I use the letter F for an element of V. How does evaluation at X act on F? It sends it to f of X. So this evaluation of X, which sends F to f of X, therefore becomes an element of V star, and the claim is this is the map, and the rest is rather routine to check, right? You check that the G action here and here. Here, of course, there is a contra-gradient action on V star that is induced from the action of V, and that V is a sub of this, so you know how it acts on Kx, and therefore how you know how G acts on V, and therefore how you know how it acts on V star. Then the given action of X, and you can check that this is G equivariant, right? And the fact that this is a closed sub, as many of you correctly said, is because you will get a reverse map in the reverse direction, Kv star to Kx, which is just the fact that all the generators, you have if there are S generators, say, if there are S generators, then you can take a polynomial ring in S variables and map them to the S generators, right? This is just, this is at the level, so this is at onto map at the level of reduced affine K algebras. It must have a corresponding map at the level of affine varieties. And what is that map? That is this. It is V star and not V. Right? This is what you have to observe. Because, so if you want to think of V as a variety, V is a vector space. If you want to think of that as a variety, the algebra is symmetric algebra of V star. K V star. V star is a linear function. V star square, or if you take two, f, g are linear functions, if you multiply them, you get a quadratic function and so on. So it's not symmetric algebra of V, but you have to put a symmetric algebra of V star. Okay, so to make it very, it's important, you might not have been very careful in your considerations at elementary levels, but it's important to keep the there is a V star, you have to use them appropriately at appropriate places. So if you're thinking is a vector space on which, say, G is acting, and you want to think of it as a variety, its ring of functions, you will write K of V, but it is the symmetric algebra of V star. Okay, so since I have written V for this subspace, the variety, if I think of that as a variety, it is V star and not V. And of course, if I write V here, there is no way I can write this naturally. It's only with V star I can write a evaluation text. Okay, and again on the second part, yeah, most of you got it right. Like I said, these the exam questions are not, they're just made up for an exam. I mean, there is nothing, they're not good enough questions to be put on a, say, if somebody were writing notes even, they're not good enough to be put as exercises in notes, right? I mean, it's just, I just made them up just a few minutes before the exam, so just to have some questions, that's all. So they're not good questions. But the point again I want to make is, see, don't of course it is good to say, when you want to work on an example, you have a theorem and you see the proof of the theorem, and so you say, okay, right, so I can follow the proof of the theorem in the case of this example, and I will get a proof, right? Okay, you do this only as a sort of last resort, right? You understand what I'm saying? So for example, look at example 1. Suppose I had some matrix which I wanted to write in, whose Jordan, whose semi-simple and unipotent parts I wanted to find. Then, of course, if I know the procedure for writing any matrix, and then I can follow that same procedure and I will get an answer, right? But that is one way, and it's a good way, there is nothing wrong with it. But often, proofs are written to take, like I repeat, take care of all cases, and very often that's not the way you think. You just want to write it. There is a mathematics to write, mathematics to think, mathematics to work. These are different things. So many times in practice they may be different. Okay. Here, for example, you need not go back here and worry about it. Rather, the way I would think is, look, let me just find something which is natural, some linear thing in which j ln is sitting. What is the linear thing in GL and sitting? It's M and C, right? And that's GL and C. Conjugation action is sitting inside M and C. Conjugation action. Well, this is an open thing here. This is not closed, right? But we know how to make it closed. So you put one more cross K, right? So you would, okay, you will, if you follow the proof of this, you get to this. But the point is, you can directly just think of this. Okay, there is nothing. I mean, the way I was thinking, I didn't suspect that you would follow the proof at all. I was just thinking like this. Okay, not that following the, again I repeat, not that following the proof is bad, but you could also do it directly. And the point is, there are other approaches. Not, proofs are just for the sake of getting a theorem proved, right? Convincing, okay, just to make sure that it's all right. But once you have done it, it's good to think of many other means of doing things. Perhaps as we don't write. I mean, of course, things are changing with the advent of so many computer programs, etc. You're forced to write programs to get things to work, for large examples, etc. Then you are not worried so much about the proof. Rather, you are worried about an efficient way of getting something done, right? That's these days a very important aspect of mathematics. So you just write this, and so here is this is a G equivariant embedding. So here A goes to A comma determinant. Should I write inverse of A? Maybe. This is the map. And the action of this is conjugation. And what is the map of G on this? So here is my X, here is my V, right? V is how many dimensional? N square plus 1 dimensional, right? So V acts linearly on this, okay? And V acts linearly on this. I'm asking for the action of G on, what action of GLN should I take on this? Trivial action, right? I should take trivial action here. And you can check that this is a, so this is a G equivalent action, I claim. How does it act here? It goes GA G inverse. Well, here if I take the image and write, I get GA G inverse, and since it's trivial, it's determinant A, inverse A. If I take the image of this, I get GA G inverse and determinant inverse of GA G inverse. But determinant inverse of GA G inverse is just determinant of A, so in fact these two are equal. So it's a G equivariant map, and we are done, right? You just needed to write this. I mean, you could write this just directly. Okay, and okay, the final problem was just a set theoretical problem. I mean, I couldn't think of a nice example of an application of constant Rosenlicht, where it says, many of you remember, I mean, but many of you did take the, sort of had done the work, and you remember the theorem and you even quoted it, which is good, which is satisfying for me. Namely that if you have a unipotent group acting on an affine variety, then all orbits are closed, right? I repeat, so the arguments in, say, the Burnsides, or rather the group theoretic angle, the constant Rosenlicht, etc., they are worth, and other things too, they are worth this, for example, right? They are worth looking at it again and again, okay, because it is these ideas rather than the statements themselves, it is the ideas behind them that keep getting used. The statements too, but once we are, the ideas behind them are also keep that's a good you will gain facility if you just. So I would recommend that you sort of go over those in your minds, or just write it out a few times for yourself, so that you make sure that you understand it. Okay. Okay. So there the point was that all the orbits are closed, and as some of you pointed out, you don't need to use the theorem at all. It's sort of obvious that all orbits are closed, and it's just a simple set theoretic checking, so I will not do it. So you had some, so if you, it was given strictly upper triangular matrices, so you take A, B, C like this, and the point was, if A and C were 0, that is, so if this is my B axis, so A and C and 0 means I am on this line, then each point by itself was a singleton orbit. Okay. But if I went out of this, took something here, or where A is non-zero or C is non-zero, or where A and C are something, then A and C won't change, but you get all B's, so you get the whole line. Right. So this, you can even draw a picture, right? You can, and it's easy to imagine. So on this line, on the every point is closed, otherwise all the orbits are lines, which are vertical lines. So they are visibly closed. Everything is closed. Okay. 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 So that does the exam. Also, Shayanto, I still haven't answered your question. Can you remind me once again what the question on the question on torus you asked me that day we went to my office and didn't do. I wanted to work on it a little bit, because I haven't given, I promised I would give you an answer, but I haven't given. So can you remind me which
The map about extra h to extra g was answered. G to h was injected, and what happens to extra g?
Then phi star is surjective, respectively injective. That's so number 2 in.
That was one question. The other thing was x with the perpendicular.
Ah, okay. So that was a mistake, right? That we decided was a mistake. But then there was a define. Okay, why it has no. Okay, now I get it. So that's fourth part. Okay, so I will think about it and give you an answer to that. Okay, that's due on my part. Okay, now okay, now let's go to right. Okay, so I gave you some homework on. Yes, you have.
I have a question.
Yeah, sure.
If you have a K to be algebraically closed field
Hmm.
and F to be a subfield,
Hmm.
and I have a set of linear equations over F,
Hmm.
which have a solution over K, then I have a solution over F.
Yes.
Can you tell me how to what's the proof of this?
Okay. One way is think of row reduction.
That's for finite, but if I have a set to be infinite, then we have to.
I see. Is that your okay? Row reduction would be all right if it was finite. No, infin and wait a second. Did we use it anywhere?
Actually, last time you gave that homework problem. T of K tensor F, T of X F isomorphic Q.
but there the number of equations may be infinite, but all the things are happening inside a finite dimensional vector space.
I need to, so that isomorphism, if I have finite dimensional generators, then it's fine. But if F is not perfect, I have to use number, definition number 2. It says Ix is J extension.
Yes. So what is the exercise I gave?
K tensor
So K tensor
TXF is
Tx x. So Tf, did I write?
no, tensor over F.
Tensor over F. This was
F,
T.
where,
What was the notation for this?
T small is capital S and then adds
Bracket F, huh? Yes. This is the claim, yes.
suppose F is not perfect.
Suppose F is not perfect.
Then you have to use the definition 2, where Ix is J extension.
Yes.
So I don't see how to do this.
Okay. So can I also think about this and let you know? Yeah. So since you have thought about it and the issues may be involved, so I'll let me think about it. And so so you want to prove this even when F is not perfect. Okay, the issue is okay. Good. Yeah, good question. Yeah, good. I'm happy these things are bothering you. Okay, so we were doing 1.4.3. I'd asked you to read up, right? So there is the notion of a regular function on a affine variety, right? So so you might have heard of a rational function in school even, right? One polynomial by another polynomial, right? So regular function is like that. You have if you have an affine variety, so let me not write it very precisely, so because it's there in the book. It's of the form f by g, where f is a f belongs to kx, that is a ring of functions. G belongs to kx, and g is non-zero at the point x. Okay, so such a thing you call regular in x, or regular. I would have preferred regular at x, but for some odd reason he says regular in x. Okay, be that as it may. So there was an exercise towards the end which says that if I have x is an affine variety and x is a point of this affine variety, and I repeat, while we are worried about tangent spaces to points on varieties, we need only be concerned about affine varieties and points on them, because whatever our definition of a variety, we haven't given it, it will surely be locally isomorphic to an affine variety. Therefore, and all the considerations will be local, so you need not worry about, naturally, because if I'm worried about tangent space at a point, what happens far away from the point is irrelevant. Okay. So there is no loss of generality in thinking only of affine varieties and points. This is a point on that variety, and mx is the maximal ideal of functions vanishing at x, right? So this is the ring of I don't know if this is what we wrote. That's the standard rotation. OXX indeed. So this had a definition. And so this is an exercise. Okay. So again, if you haven't done that exercise, you should go back and do this. So there is and if there are any questions, please do raise them. Okay. And so we had several definitions of the tangent space, right? So So Txx was what? Derivations of k derivations of kx to, this was one of them, and then this was another, right? And then what? Or if you want, where this denotes, this may not be the notation of the book, I don't know, but this is the maximal ideal of the ring OXX. This is a local ring. Oh, I can even write MX. Right? If I have this, therefore this is a local ring with maximal ideal MX extended to this. So I can write that. Okay, and we also had this, right? Hom as k algebras of that lifting x. So where x was the point x you think of as giving you the map kx2. So this remember, x is just a algebra homomorphism from kx to k, right? So that's what you call. So this should lift, meaning if I compose this further with k, I mean there is a natural map here to k where t goes to 0. So this lifting x means all those algebra homomorphisms here, which when I compose further with the natural morphism putting t to 0, I should get this one, right? So this is the definition of tangent space using dual numbers. This is using derivations. This is called Zariski tangent space, and we were left with showing that this, I mean we had seen sort of that maybe these two were equal. We had claimed that this was equal. I didn't prove that, and the next one is this, right? And again, I won't prove the inequality here, it's rather boring to do that. The point is, see, what does this look like? What is that? Let's just intuitively see what it means. What do I have here? What is the difference between this and this? It's the same, except that here instead of kx, I have kx localized at mx. That's all I have. So this is the same. This is actually equal to kx. As you know, if I have a ring modulo a maximal ideal, or ring localized at the maximal ideal modulo the maximal ideal extended to the localization, is the same as just the ring modulo the ideal. So this or this doesn't make a difference. It's the same. So the only difference between this and this is that this is localized at the maximal ideal. Okay, but then the point is, if I give you a derivation here, it extends uniquely to a derivation here by the quotient rule. And what is the reverse map? I just restrict that derivation. This is a sub of that, so I restrict the derivation. This is as simple as that. So no further, the rest is just routine checking, and I leave it. It's a pleasant and easy exercise that can be safely left to you. Okay. So next time we will start with differentials and separability. Like I said, this is abstract commutative algebra, which in many commutative algebra books, commutative algebra books like Matsumura, is done just from the point of view of commutative algebra, which while it is understandable, it is also important to keep what they mean, what these constructions mean geometrically, right? They are trying to, as I repeat, we are trying to do algebraically something, we are trying to do calculus algebraically. That's what we are trying to do. Okay, we are trying to differentiate, find different, right? Okay, so it's interesting to see that not only can it be done, but in fact it can be done very well, so that it applies in the usual case of complex numbers or real numbers, but also applies in other cases. Okay, and even if you wanted to think of calculus, you get a fresh look at it, because you can throw away what you know and keep this, and you can still recover whatever you know, and with more clarity. Okay, good. And as I said, it is there are some non-trivial statements in field theory that we will encounter. So we meet on Friday. Yes, Friday. Yes. So we continue from there on Friday. Okay.